Welcome to The Debate. If you were to crack open almost any piece of electronics you own, your smartphone, your car's engine control unit, even that smart coffee maker on your counter, and you peeled back all the layers of digital processing, deep down, you're going to find an analog backbone. We are talking about signal conditioning, and the absolute king of that jungle is the operational amplifier, or OPAmp.
It really is. It's the component that bridges the gap between the messy, chaotic physical world and the clean, binary digital world we prefer to live in.
Exactly. Now, our source material for today described them as high-performance building blocks. That sounds straightforward enough, but we aren't here to just read the datasheet or memorize pinouts. We are here to debate the philosophy of how you actually understand and utilize these devices. When you sit down to design a circuit, what is your mental model?
Right. It's a question of perspective. Do you view the op-amp as a pure mathematical abstraction that's defined by universal theoretical laws? Or do you see it as a collection of specific functional tools, like a screwdriver, a hammer, a wrench, where each topology has its own distinct quirks, limitations, and, gotchas?
I am taking the position that there is only one way to truly understand an op-amp: the ideal rules. The source material lists them explicitly as the foundation. My argument is that if you deeply understand zero input current and zero differential voltage, you don't need a cookbook of circuits. You don't need to memorize formulas. You can derive the universe from scratch. The power lies in the theoretical universality.
And that is exactly where we diverge. See, I am arguing for the essential circuit derivations approach, the topological view. The physics might be universal, but engineering is all about trade-offs. If you ignore the specific architecture, whether it is inverting, non-inverting, or differential, you might get the algebra right, but you will build a circuit that just fails in the real world. You can't derive your way out of a blown component.
Fair enough. Let's get into it. I want to start with my core thesis, which is really about the power of first principles.
Lay it out.
The source material presents a graphic with the ideal op-amp rules right at the top left. This isn't just an introduction. It is the DNA of the entire field. Everything an op-amp does, every complex filter or regulator you build, it all rests on two critical assumptions. Rule 1. Assume no current flows into the inverting or non-inverting input terminals due to infinite input impedance.
The golden rule of inputs.
And Rule 2. Assume there is no voltage difference between the two input terminals when feedback is present. V plus equals V minus.
Simple enough on paper.
But think about what that actually means. It is a profound statement. It says the device has infinite input impedance and infinite open loop gain. When I look at a schematic, no matter how messy or complex it appears, I don't panic. I don't go looking for a reference design. I just apply those two constraints. And the complexity, it just collapses into simple algebra. Whether I am building an amplifier, a summer, or a differentiator, the behavior is an inevitable consequence of those two rules. I don't memorize that a non-inverting amplifier has a certain gain equation. I derive it in 10 seconds using the rules. It's the purest form of understanding because it relies on the internal logic of the device, not on, rote memorization.
See, that is a very elegant argument for a physicist or a mathematician, but I am not convinced it serves the working engineer. Let's look at the essential circuit derivation section of the material. This is where the rubber meets the road. You mentioned Rule 1, the no input current rule.
It is the starting point for everything.
It is a rule, yes, but simply stating the rule doesn't tell you how to exploit it. The description for the non-inverting amplifier in our source material highlights something very specific. This configuration offers very high input impedance because the signal enters the plus terminal directly.
Which is just a direct consequence of Rule 1.
It is consistent with Rule 1, sure, but the value is in the topology. Let's make this concrete. Let's say I am designing a medical device to pick up a fetal heartbeat. That sensor is incredibly weak. It is high impedance. It can't push any significant current. Now, if I am just thinking about balancing voltages or deriving equations, I might accidentally pick a topology that kills my signal. But if I am thinking topologically, I immediately grab the non-inverting configuration because the architecture itself exposes that infinite impedance to my sensor. The ideal rules don't warn you about loading effects. Only the specific circuit architecture does.
I think you are creating a false dichotomy there. The rules do warn you if you listen to them. If you assume no current flows, you implicitly understand the impedance. But this actually leads us perfectly into our first major clash, the mechanism of amplification itself, specifically the summing point.
The virtual ground. I know you love this concept.
I do. In the foundation section, there is a specific call-out for this. It states, in most negative feedback circuits, Rule 2 creates a virtual ground, or summing point, where currents are balanced to zero. To me, this is the most beautiful concept in analog electronics.
Beautiful? Maybe. Practical? Let's discuss.
Look at the inverting amplifier diagram. You have an input resistor, let's call it R1, and a feedback resistor, R2. Because of Rule 2, the negative input is locked to the positive input. Since the positive input is grounded, the negative input is at 0 volts. It is a virtual ground. It is not connected to the earth, but it acts like a sinkhole for voltage.
Right. It forces the potential to 0.
Exactly. So, the math becomes incredibly simple. The current coming in through R1 has nowhere to go but out through R2 because Rule 1 says it can't go into the op-amp. In plus I feedback equals 0. You are just balancing currents on a teeter-totter. The op-amp turns voltage into current, balances it, and turns it back into voltage. When you understand the summing point, you realize the op-amp is an active participant constantly fighting to keep that balance. It gives you a sense of the device's agency.
I am not denying the math is elegant. The transfer function comes out cleanly. Vout equals negative R2 over R1 times Vn. It is a perfect linear relationship. But here is the problem with viewing the world through the summing point. That virtual ground is a trap.
A trap? How so?
Think about where the signal goes. In that inverting configuration you love so much, where does your signal travel? It travels through R1 directly into that virtual ground. That means the input impedance of your entire amplifier is set by R1. So if you need a gain of, say, 100, and you pick a 1K resistor for R1 and a 100K for R2, your input impedance is 1K. That is shockingly low for modern electronics.
So you use larger resistors.
You can't just scale them to infinity. You get Johnson noise, you get stray capacitance issues. My point is, if you use the inverting topology, you draw current from your source, you load down your signal, you distort the very thing you are trying to measure before you even amplify it.
That is a design choice, though. It is not a flaw in the rules. It is a variable in the equation.
It is a topological limitation. Now, contrast that with the non-inverting amplifier. As the material states, the signal enters the plus terminal directly. This utilizes the infinite input impedance of Rule 1 to preserve signal integrity. If I am a listener connecting a piezoelectric guitar pickup or a pH probe, the inverting amplifier's summing point is going to ruin my measurement. I need the non-inverting topology. The shape of the circuit matters more than the math used to solve it.
But notice what you sacrifice for that protection. Look at the transfer function for the non-inverting amplifier. Vout equals 1 plus R2 over R1 times Vin. Notice that 1?
Sure, it is gain plus 1.
That 1 is a prison. You cannot have a gain of less than unity in a non-inverting configuration. You can never use it to attenuate, to shrink a signal. It can only make things bigger. With the inverting amplifier and the summon point, if I make R2 smaller than R1, I can shrink a massive voltage down to something safe for a microcontroller. I have total mathematical control. The ideal rules explain exactly why that 1 exists. It is the input voltage appearing at the feedback node.
That is a valid point regarding attenuation. If you need to scale down a 10-volt signal to 3 volts, the inverting topology is your friend. But I would argue that most signal conditioning tasks, as described in the intro, are about taking weak signals and making them strong. And usually that plus 1 is negligible when you are designing for a gain of 500 or 1,000.
Negligible until it saturates your rail, maybe. Precision matters.
Touché. But my point stands. If you start with the summing point as your gospel, You might build a circuit that destroys your signal quality before you even amplify it, all because you ignored the impedance characteristics defined by the topology.
I think we can agree that impedance is critical. But let's look at a circuit where the ideal rules really flex their muscles. The differential amplifier. The material shows this as a mix of 4 resistors and 2 inputs, V1 and V2.
This is the staple of instrumentation. Every industrial plant runs on these.
The transfer function is V out equals R2 over R1 times the quantity V2 minus V1. This is the ultimate proof of the rule's power. How do we get there? We don't memorize it. We apply Rule 1 and Rule 2 simultaneously. You have voltage division happening at the positive terminal, and the virtual short transferring that potential to the negative terminal. It is a symphony of Rule 1 and Rule 2 working in concert. The op-amp is amplifying the difference between 2 points. The theory holds regardless of what those inputs are.
It is a beautiful derivation, I grant you that. But why do we use it? The source material gives a very specific use case, such as the offset of a Wheatstone bridge.
A classic application. Strain gauges, pressure sensors, load cells.
Right, but think about what a Wheatstone bridge actually produces. It produces a tiny, tiny voltage difference riding on top of a massive common voltage. Maybe you have 2.5 volts on one wire and 2.501 volts on the other. You only care about that 0.001 difference. The value of the differential amplifier isn't just a subtraction. It is the rejection.
Common mode rejection?
Exactly. It is like being at a loud party. The common mode is the background music and the chatter. It is everywhere. The differential mode is your friend whispering in your ear. The differential amplifier's job is to ignore the party and amplify the whisper. The ideal rules give you the subtraction equation, but they don't explicitly teach you about the common mode rejection ratio, the CMRR. That is the hidden hero here.
But the rejection is implied in the subtraction. If V1 and V2 both rise by 5 volts, that is the party noise, the difference remains constant. The quantity V2 plus 5 minus the quantity V1 plus 5 is still just V2 minus V1. The math is the rejection. You don't need a separate concept for it. The rules handle it automatically.
In an ideal world, yes. But the essential circuit derivations imply something practical. Look at the resistors. You have to match those ratios perfectly. If the R2 over R1 ratio on the top doesn't match the bottom to within, say, 0.1% or better, the subtraction fails. The party noise leaks through.
Of course, component tolerances matter.
They matter enormously. If you rely only on the ideal rules, you assume the components are perfect. You derive the equation and go to lunch. But the topology mindset knows that the physical implementation is fragile. If you don't use precision resistors, your expensive differential amplifier becomes surprisingly bad summing amp. The topology dictates the precision required. The dissenter focuses on the difference because that is where the information lives, separated from the noise.
That is an interesting perspective, though I would frame it differently. The rigorous requirement for resistor matching is simply a demand that we respect the math. If the ratios don't match, you are not building the equation V out equals R2 over R1 times the difference. You are building a different, messier equation. So sticking to the ideal rules actually forces you to recognize when you've deviated from the design.
A fair counterpoint. Let's move to the quick reference table at the bottom right of the material. This is where we see the transition from static voltages to dynamic functions. Things get interesting here.
I love this table. Look at the summing amplifier. It lists the output as the negative sum of multiple inputs. V out equals negative V1 plus V2 and so on.
Scaling and adding multiple signals, as the text says.
This proves the op-amp is a mathematical engine. It is literally doing arithmetic, addition. This goes back to my point about the summing point. You are taking multiple currents from different sources, merging them at the virtual ground, and producing a result. It validates that the core function of an op-amp is computation. In the old days, before digital computers, these things literally were the computers. They calculated trajectories and simulations.
That works for this summing amp because it is just resistors. It is instantaneous. But look at the next entry, the integrator. The transfer function changes completely.
We see an integral symbol, the integral of Vn dt. We have introduced calculus. We have introduced time.
We have introduced a capacitor into the feedback loop.
Correct. And the primary use listed is producing ramps or smoothing data. This is a crucial distinction. Smoothing data is a time domain concept. It means taking a jagged, noisy signal and averaging it out over time. If you only look at the ideal rules, which state that V plus equals V minus, you miss the dynamic behavior.
I disagree completely. The integrator is still just the ideal rules applied to reactants.
How so?
The rules don't mention time, but physics does. A capacitor has an impedance, just like a resistor. It is just 1 over j omega c. If you plug that impedance into the standard inverting amplifier formula we discussed earlier, replacing R2 with the capacitor, the math naturally transforms from multiplication to integration. The ideal rules don't stop working just because you added a capacitor. They perfectly predict the ramp. If you put a constant voltage in, you get a constant current. That constant current fills the capacitor linearly, hence a ramp. The physics of the capacitor plus Rule 1 and Rule 2 equals integration.
That explains the ramp, sure. But smoothing data? That requires thinking about frequency response. It requires thinking about the circuit as a low-pass filter. The essential circuit derivations mindset looks at the integrator and asks, what is the bandwidth? Where is the cutoff frequency?
But you cannot calculate the cutoff frequency without the derivation.
You can if you understand the function. Think about it. At DC, or zero frequency, a capacitor is an open circuit. It's a broken wire. What happens to your inverting amplifier when the feedback loop is broken?
The gain goes to infinity. Or, well, the open loop gain of the OPAmp, which is massive.
Exactly. The thing saturates. It hits the rail. The ideal rules say V plus must equal V minus, but if the feedback loop is blocked by a capacitor at DC, the OPAmp can't maintain that balance. The rules break down, or rather, the physical limits of the chip take over. You need a parallel resistor to provide a DC path, a topological fix for a physical problem.
I see what you were saying. You were saying the topology implies the stability requirements?
Yes. When a user is looking at this infographic to design a noise filter, they're looking for the functional outcomes smoothing, not just the raw calculus derivation. They need to know that the bucket, the capacitor, will overflow if they don't poke a hole in it with a resistor.
That is a vivid analogy. The bucket will overflow. I suppose I see the capacitor as a variable in a differential equation, and you see it as a water tank.
And both are true. But the water tank analogy keeps the smoke inside the chip.
Let's look at one more from the quick reference, the voltage follower. V out equals V in. Why is this even here?
Ah, the buffer. My personal favorite.
It is the trivial case. It is a non-inverting amp where the feedback resistor is 0, just a wire, and the ground resistor is infinity, open air. The formula 1 plus R2 over R1 becomes 1 plus 0, which equals 1. It is mathematically redundant. It changes nothing. The output is exactly the same as the input.
Mathematically redundant, perhaps. But functionally, it is vital. The primary use is listed as impedance matching isolation. This highlights my central thesis perfectly. The ideal rules allow you to calculate that the voltage doesn't change, but they don't tell you why you would bother building it.
Because of Rule 1?
Exactly. It bridges the gap. It takes a signal that is weak and fragile, high impedance, and replicates it perfectly, but now backed by the muscle of the op-amp's output current. It separates a weak source from a heavy load. It is a bodyguard for your signal.
A bodyguard? I like that. I would argue that understanding why it works as a bodyguard comes directly from Rule 1. Infinite impedance. The voltage follower is the physical embodiment of Rule 1. It says, I will look at your voltage, but I will not touch your current.
It is Rule 1 on the input and ideal voltage source on the output. It is the ultimate translation layer between the theoretical ideal and the messy reality of loading effects. If you just look at the math, you see x equals x and think it is useless.
If you look at the topology, you see the most useful circuit in the catalog.
We are nearing the end of our time, so let's try to synthesize this. We have looked at the inverting amp, the differential amp, the integrator, and the follower.
We have covered a lot of ground.
My position remains that the foundation is the key. If a listener understands zero input current and zero differential voltage, they possess the skeleton key for analog electronics. They can look at any circuit, even one they have never seen before, and break it down to its elemental truth. The quick reference table is useful, but it is just a list of consequences of those two rules.
And I maintain that while the rules provide the math, the essential circuit derivations provide the engineering context. Knowing that V out equals negative R2 over R1 times V in is one thing, but knowing that the inverting topology creates a virtual ground that might load your sensor, while the non-inverting topology protects it, that is the critical knowledge gap. The choice between these configurations determines the success of the signal conditioning, not just the correctness of the algebra.
It seems we have an interesting duality here. The material presents the op-amp as a theoretical construct that obeys strict laws, and simultaneously as a set of practical tools, hammers, screwdrivers, and wrenches, that we use to manipulate signals in the real world. You need the rules to make sure the math works, but you need the topology to make sure the circuit works. Perhaps that is the takeaway. Use the ideal rules to verify your understanding, but use the essential circuit derivations to guide your design choices. Don't be afraid to derive, but don't forget to check the map. I can agree with that. The map keeps you from driving off a cliff or blowing up a capacitor. We hope this debate has helped illuminate the different layers of understanding available in this material. Whether you're a fan of first principles or a topological pragmatist, the op-amp remains a fascinating subject.
Indeed. I encourage our listeners to take a hard look at that quick reference table and ask themselves, do I see a math equation or do I see a signal processing tool?
Thank you for joining the debate.
Until next time.